Now we're going to talk about something called the mean value theorem. And I'm going to split this video up into two parts. The first part is going to be mostly about the mean value theorem. I'm going to do an example of how the mean value theorem works and how to prove this part right here for a problem. And the second one, we'll be talking about all the different parts or what it means if a function is increasing or decreasing on an interval or whatnot, then do an example of that. So first of all, the mean value theorem, it connects the average, get the highlighter, the average rate of change of a function over an interval with the instantaneous rate of change at a point. So this is really important because it connects what we've done in algebra to what we do now in calculus. Okay, remember they're kind of the same thing. The only difference is that the average rate of change of a function, in like algebraic terms, is you find the slope between 2 points. So that would be like y1 minus y2 all over x1 minus x2. Whereas now, the instantaneous rate of change, that's the derivative, and so then that would be f prime of x. They mean the same thing, but in order to find the average rate of change, you need 2 points. Instantaneous rate of change, you just need 1 point. All right, so let's look at the mean value theorem. It says if you have a function, f of x, and it's continuous at every point on, again, the closed interval, and differentiable at every point on its interior, then there's at least 1 point c. And you notice this is not inclusive, it's exclusive, because the function is not differentiable at an endpoint. So just remember that. That's why this is it's not inclusive, but it does have to be on a closed interval. It says then there's at least 1 point c in a to b. So you notice that this c cannot be equivalent to a or b. So it cannot be equivalent to a or b. It's somewhere between them. At which, now in this case, all this is saying is that, let me get this eraser and erase this, is that this is the derivative at a point So we're saying the derivative at a point is equal to the slope of the secant line. Okay, derivative at a point. So that's calculus. This is our connection. This is calculus, and this right here is algebra. All right, so then this is f prime of x on the left side. On the right side, that's you finding the slope. That's the slope of the secant line. So here we are. Here's a line. Here's A. Here's B. What this is saying is that if we draw the secant line, so that's the line between A and B, it has to have the same slope of a tangent line. So it looks like it'll be right about here. If I draw a tangent line, those two lines are parallel, and that occurs at least once on an interval. If I drew an infinite number of, tangent lines in here, one of them is going to be parallel to that secant line. That's what the mean value theorem is saying. And there's all sorts of applications to this. So it's important we understand what it is, and then also that it's an existence theorem. So it tells you something exists without ever telling you how to do it. Okay, so here it is, and there's no real explanation of how to do it, but we know how to do it. Okay, we're going to do an example of that. So here's our example. Get rid of that. There we go. First thing we need to do is figure out what our different parts are. So let's do this one in green. We're going to find the derivative at c. C and x are interchangeable. We don't use x because x is on the interval, but c has to be somewhere between a and b. Okay, so really when we're asked to find f prime of c, we're asked to find the derivative of the function, whatever that is. Okay, so the derivative of the function is equal to, when we find the derivative of this, it's going to be 2/3 x to the negative 1/3. I'm going to rewrite that. This is going to be 2, let's just do, okay, I see. So instead of doing this, let's just go ahead, and keep it like this. You'll see why later. And then I'm going to go ahead and do this one in blue. So f of b minus f of a, so that's going to be f of 1 minus f of 0 all over 1 minus 0. When I plug 1 in there, that's 1 to the 2/3 minus 0 to the 2/3 all over 1 minus 0. And then when I simplify this, that just gives me 1 over 1 or 1. Now I'm going to go ahead and set these equal to each other. So you would then have 2/3 x to the negative 1/3 equals 1. Multiply each side. By 2/3. Or not 2/3. Sorry. 3 halves. There we go. 3 halves. Multiplied by the reciprocal. That way those disappear. And so you'd have x to the negative 1/3 is equal to 3 halves. Now, here's the tricky thing. We want to get rid of that exponent. And so what we have to do is power each side to the positive 3 over 1. Or just to the 3rd, whatever. But remember, exponent to an exponent, you multiply. So negative 1/3 times positive 3 over 1 is 1. So this becomes an x to the 1st. And then this here, wait a minute, no, negative times a negative. So this is going to be a negative. Let me change this. So this has to be a negative because the negative times a negative is a positive. So this has to be a negative. There we go. So this negative reciprocates, so then this becomes 2/3 to the 3rd power, got rid of that negative there, and then 2 to the 3rd over 3 to the 3rd, that becomes 8 over 27. And so what that means is that our C value, the value between A and B, is going to be 8/27. So here's the graph of our function. If we could draw a line, so imagine I can't on this, but draw a line from the point where my cursor is to there. You'd have that secant line at about 1/3, so just under 1/3. If we drew a tangent line there, that would be the exact same slope as that secant line. So that's what we're finding when we're using the mean value theorem, and that's what we're proving, rather, when we use the mean value theorem. Okay, so there's another problem very similar to this, just uses sine, inverse sine rather. So go ahead and try this one on your own, and then come back and see how you did. So if we look at this, we can go ahead and start it. The inverse sine at 1 is pi over 2. The inverse sine of negative 1 is negative pi over 2. And there's other, you could also use 1, 2, 3, 4, 1, 2, 3 pi over 2. It'll work the same way. But we'll use negative pi over 2. So we can go ahead and simplify those. I found the derivative of inverse sine, which is 1 over the square root of 1 minus x squared times the derivative of x, which is 1. It's an identity we learned. Then the inverse sine of 1 is pi over 2, minus the inverse sine of negative 1 is negative pi over 2, all over 1 minus 1, that's equal, or 1 minus a negative 1, that's equivalent to 2. And then this becomes plus a positive as well. And so then that becomes 2 pi over 2, which is pi. And then this 2 just comes over. Now what we're going to do is we're going to go ahead and set these equal to each other. So we have to show that this, or we know the mean value theorem tells us that these two parts are equal to each other. So we're going to go ahead and set them equal to each other and solve. So you'd have 1 over the square root of 1 minus x squared is equal to pi over 2. To make this easier to work with, I'm just going to reciprocate each expression on each side. As long as I do the same thing on each side, it'll be fine. That way, on the left side, I just have the square root of 1 minus x squared. And then on this side, I have 2 over pi. Then what I'm going to go ahead and do is I'm going to square each side, because I'm trying to undress this equation, so to speak, to solve for x. So then you would just have 1 minus x squared is equal to then 4 over pi squared. Then if we come down here, extend the page a little bit, you would go ahead and subtract 1 from each side. So don't forget, that's still a negative x squared. So you'd have negative x squared is equal to 4 over pi squared, then minus 1. Now what we can do is go ahead and multiply everything and change all of our signs, multiply everything by a negative. Now we have that, and we want to go ahead and take the square root. That'll be the last thing that we do, so that's a positive. And we're going to take the square root of that. And we go ahead and look at this. So our answer then, you would get x is equal to, when you go through and take the square root of that, you get 0.771. And also you remember, back here we took the square root, so then our answer should be, get back again, positive and negative. If we look at the graph, we're going between -1 and +1, so if we connect those points, we should have 2 tangent lines, one about right here, the other one about right here, that would have that exact same slope of that secant line. So anyway, so that's the mean value theorem. That's all I wanted to do for this video. Just an introduction to the mean value theorem, what it says and how it works, and the fact that it's an existence theorem. So there's still work that we have to do to show that it's true or whatnot. And I guess the other part of these questions asked you to figure out whether or not the mean value theorem even exists, or if it satisfies, and on both of these it does, because if we look at, for example, this graph, in order for it to satisfy that, it has to be a closed interval, which is what they gave us on the problem. And then also it's got to be continuous, and you notice this is in fact continuous. So the interval was closed, which that was closed, and we know that this inverse sine function is continuous at least from -1 to 1.